Hey guys, welcome to Chemistry in my sunroom. Hopefully you guys can see pretty well, and also I hope it's not too noisy. My kids are having a wonderful day running around outside, and all the chickens are out, so it's possible that we are going to get interrupted by a screaming child or a rooster out on the deck. We'll see. But hopefully we can talk today about nuclear chemistry. So this is coming from the Chapter 25 handout that I gave you guys on last Monday, and all of Chapter 25 is due on Friday by 9 p.m. So the first thing I want to talk to you guys about, besides saying hi, is radiation and decay. Radiation is just the fancy chemistry way of saying that energy is being released from a nucleus. That's where nuclear chemistry comes from. We're talking about that teeny tiny nucleus at the center that's full of protons and neutrons in the center of an atom. When protons and neutrons leave that nucleus, it takes with it a lot of energy, and it also changes the identity of that atom. So that's what radiation, alpha radiation, beta radiation, gamma radiation, that's what all those things are dealing with. Decay is just a spontaneous falling apart of a nucleus. I'm going to talk about alpha radiation here, only because once you have this concept, it's not hard to switch out the alpha particle for a beta particle or a gamma particle. All of these are described in the packet that you have. We're looking at page 800. So you can think of a radiation problem as just a subtraction problem. One of the most common elements that undergoes this kind of radiation is uranium. Uranium-238, 92. Hopefully you guys remember at least a little bit about how we write molecular symbols. So you remember that the letters actually tell you which element you're working with. 238, the number on top, that is the mass. So that's the protons and neutrons. We will circle that. At the bottom, 92, that is the number of protons. This is going to be important because this is going to change when the element decays. So you can think of decays as a subtraction problem. When we're talking about an alpha particle, we're talking about a particle that has 2 protons and 2 neutrons. 2 protons and 2 neutrons. 2 protons and 2 neutrons add up to be 4. And down here we're going to write that we have 2 protons. That of that 4, two of them are protons. We then do a subtraction problem from across the same types of numbers. So here you have atomic mass, here you have atomic mass. 238 minus 4 is 234. Here you have number of protons, and here you have number of protons. 92 minus 2 is 90. This is all the math you have to do. Yay! Once you have done this math, once you've figured out the total atomic mass and the new number of protons, then you'll check your periodic table and see, okay, what is number 90 on the periodic table? Number 90 on the periodic table happens to be thorium. Let me help you guys zoom in here, okay? So this is just a giant subtraction problem. We had uranium, we subtracted an alpha particle, and we got thorium. Simple as that. To change this into a balanced equation, I'm quite simply going to turn my subtraction sign into an arrow and turn my equal sign into a plus. Now I have a balanced equation. Uranium-238 spontaneously releases an alpha particle and becomes thorium. That's all there is to radiation and decay. You may switch out your alpha particle for a beta particle or a gamma particle, but the method is the same. Let me know if you guys have any questions.